Well, hello everybody. It's been a while since we've been working together on videos, so I'm excited to be back. So tonight's video is on more on systems of equations, which we've been working on in class. But today we're going to learn the third method. So far we've learned how to solve a system by graphing, and we've learned to solve a system by using the substitution method. The last one that we're going to talk about before we go on to applications of all this is it's called the elimination method. It's also known as linear combination. But we're going to review. Let's review a little bit. A set of equations that have a common solution is called a system of equations. We've been specifically looking at a system of linear equations, which means that we're going to have two equations and two variables. We know they're linear because the highest exponents that we're seeing is a 1. We should know at this point that a solution to a system of two equations is a coordinate point, an xy coordinate point that makes both equations true. And we've talked a lot about how it really is the point of intersection on the graph. Point of intersection of the graph. So all of that should be stuff that you remember, we've talked about. All right, so now you've learned how to use to solve systems of equations by substitution. We want to still use this method if one variable has a coefficient of 1. That's going to be the best time to use substitution. If it doesn't, then you can get into fractional issues, and we want to be careful there. Okay, so let's talk about elimination. First of all, if you're going to use elimination, you want to make sure that one variable, and it can be either one, is or has the same number in front of both of them and opposite signs. And I'm going to show you what I mean by that in a second. If you have two variables that have the same number in front of them but they're opposite signs, it will help because you can add the equations together, and one variable will then get what we call eliminated. And I know that can be confusing when we write it out, but I'm going to show you in a second. All right, so let's look at an example. I'm going to give you a second actually to write that, because I know I'm moving a little bit fast. All right, so you should be writing. And now here's what I mean. I've got a system, it's two equations. Now I know I told you if one of the variables had a coefficient of 1, you're going to use substitution, but I'm going to show you elimination using this. So I look at it and I see that the y and the y in the top and the bottom both have a coefficient of 1 in front of them, so the number is the same, but they are opposite signs. Okay? If they have the same number and they are opposite signs, then we can add the equations together. So we would have x plus x, which would give me 2x, 1y plus a negative y, which means 1y minus y. It would get eliminated. It would go to 0. And then you have 5 plus 1, which would give me 6. Divide by 2 on both sides. So then x would be 3. How do we find y? We take our x, we plug it back into either equation. So I'm going to plug it in to the first equation. Remember, when we plug something in, put it in parentheses. Okay. Subtract 3 from both sides, and so y equals 2. Then we take our points and we put them in a coordinate. So my answer is 3, 2, and that is where these two lines intersect. They're going to intersect at the x of 3, the y of 2 on a graph. Okay? All right. So we're going to go through the 3 things that can happen. Not all equations are so nice and clean. There's 3 different things that that can happen with elimination, and on your note sheets, we're going to go through each one of them. Okay. So our first one. Scenario 1 is when we just add. We're going to look for the variable or variables that have same coefficient but opposite signs. Okay? So while you're writing that, I'm just making sure that you guys can see everything that we're doing on the graph. Okay, perfect. So I look at it and I see I've got 2y and a negative 2y, so I have two variables that have, or the variables that have the same coefficient, opposite signs. So this is scenario 1. That means we just add the equations together. Okay, and I put a plus here and I make a line because I want to make sure I add every single piece of the equation together. So x plus 3x gives me 4x. 2y minus 2y, because it's plus and negative, gets eliminated, and then 5 plus 7 is going to give me 12. Okay, then we divide by 4 on both sides, so then x is 3. What do I do now with x? I take x and I substitute it back in to either one of the equations. It's easier in the first equation, so I'm going to put in 3 plus 2y equals 5. Subtract 3 from both sides. So we get 2y equals 2. Divide by 2 on both sides. So y equals 1. Hopefully you're seeing that. Then we write our answer as a coordinate point, 3, 1, and then we box it. So 3, 1 is the coordinate point where these two lines intersect. It means that if I plug 3 and 1 into each equation, it will be true in both of them, okay? All right, so I want us to try one now. So we're going to try this next one. I want you to go ahead and try it. I want you to press pause, and then I'm going to come back and do it for you, okay? So you should be pressing pause at this moment. All right, I look at it. I have one variable. In this case, the a term is both same coefficient, opposite signs. That means I can just use adding. I add the equations together. 4a minus 4a gives me 0. It gets eliminated. 3b plus 1b gives me 4b. 7 plus 5 gives me 12. I divide by 4, so then b equals 3. I take my b, I plug it into either equation. I'm going to plug it into the second equation because it's a little bit easier for me. Negative 4a plus 3 equals 5. Subtract 3 from both sides. So negative 4a equals 2. Divide by negative 4 on both sides. And so a should have been, it reduces to negative 1/2. At that point, I go ahead and I write my coordinate point, always going to be in alphabetical order. So negative 1/2, 3, coordinate point, and there we go. And again, this is the point of intersection of these two line graphs. It's the point that makes both equations true, okay? All right, so you should hopefully got that nice practice in. We're going to look at scenario number 2. Start to get a little bit more challenging in scenario number 2 because we have to multiply one equation by a constant, and a constant's just another word for a number, and then add them. Okay, so what I like to look for is I like to look for the variables, and it doesn't have to be done this way, but I like to look for the variables that have opposite signs. If they don't have opposite signs, then I'm just going to multiply by a negative. But I looked here and I'm like, okay, y and 3y have opposite signs. I have no variable that has the same number and opposite signs. So that tells me I'm going to have to multiply either one or both of them by something. So if I multiply the top equation by the number 3, then it would make give me a 3y, so that I'd have a 3y and a negative 3y, and then I could add the equations together. Okay, so I'm going to do that. I'm going to multiply the top equation by 3, which means I have to distribute it to everything, and I'm going to write it right over here now. So we have, switch colors, 3x plus 3y equals 3. You've got to make sure that that number gets multiplied to everything. It's just really making the equation bigger, not as simplified. Then we're going to take this equation and write it directly under it. Again, now we've got two variables, or one variable that has both the same coefficient, opposite signs, so I'm going to add the equations together. When I add, I get 3x plus 2x, which gives me 5x. 3y minus 3y will get eliminated, and then I have 3 plus 12, which would give me 15. I divide by 5 on both sides, so then I get x equals 3. I take my x equals 3 and I plug it into either equation. The beginning equation is fine, so I'm going to go to the first one, and I'm going to put in 3 plus y equals 1. Subtract 3 from both sides, and I will get y equals negative 2. At that point, I take my x and my y, I write them as a coordinate point. And in your mind, I need you to be thinking, that is the point where these two lines intersect. It is also the point that makes both equations true. Okay? All right, so now you're going to try one. So you have one in your paper, 6x plus y equals negative 5, 2x minus 3y equals 10. Now, we may choose different variables to modify, but it doesn't make it wrong if we get the same answer, okay? So I want you to press pause and try it, and then come on back and we'll try it together, okay? Okay, so you've done it, and you got your answer, and I'm going to do my work here. I looked and I saw the y's had opposite signs, so I was going to multiply the top equation by 3. Okay, so that means I'm going to multiply that 3 to everything, even the negative 5 I'm not going to forget. Now, I'm going to neatly rewrite it right below it. Okay, so I'm going to get 3 times 6, which is 18x, plus 3y equals negative 15. Okay, you've got to be careful with those positives and those negatives. Then I'm going to combine these two equations using addition. Okay, so I have 2x and 18x, which gives me 20x. I have negative 3y and positive 3y, that's going to get eliminated. And then I have 10 plus a negative 15, which gives me negative 5. I divide by 20 on both sides, and I get x equals negative 1 over 4, because they're both divisible by 5. Are we there? Okay. Then what do we have to do next? What we have to do next is we have to plug our x in and solve for y. Now, I'm going to try and be careful because I've got fractions. So I'm going to go into that first equation, and I'm going to put 6, negative 1/4, putting it in parentheses, plus y equals negative 5. We simplify this, then multiply. Simplify, then multiply, so it's 6 over 1. We divide 6 by 2 and we get 3. We divide 4 by 2 and we get 2. So now I have negative 3 halves plus y equals negative 5. We're going to add 3 halves to both sides. Okay, and we have negative 5 plus 3 halves. We have to find a common denominator, which is 2. And so this becomes negative 10 over 2 plus 3 over 2. So my y then is negative 10 plus 3, negative 7 over 2. And I put them together in a coordinate point, negative 1/4, negative 7 over 2. Again, that is the point intersection of the graph. It is the point that makes both equations true. Okay? All right. I know it's a lot. Now we've got our last scenario, so we're almost there. All right, so scenario number 3. Multiplying both equations by a number and then adding. Multiplying both equations. Both equations by a number and then adding. Because look at it. We look at these and we've got no coefficients the same, and there's no way for me to make one of them exactly like the other without changing both of them. So I still look for the variables that have opposite signs, if any, or the smaller of the numbers. The smaller numbers will definitely be easier if we have to multiply both equations. So I looked at this and I'm like, okay, the 3 and the y's are both opposite signs, so I'm going to work with those just to make this easy on myself. So I'm going to multiply it, and what number can I make them both that's small? Well, they're both divisible by 6, so 6 is a common factor of them, right? So I'm going to multiply the top by 2 to make negative 3y6. And I'm going to multiply the bottom by 3 to make this 2y. It's going to become a 6. All right, so I'm going to rewrite both equations. So we're going to get, and I'm going to actually write it down here, 8x minus 6y equals 22. And the next equation I'm going to get 9x plus 6y equals negative 39. Okay, so again, I multiplied both equations by a number so that I could get one variable to be the same sign and same coefficient. Now I add them together. So I have 8x plus 9x, which is 17x. These get eliminated, and then we have negative 39 and 22. And remember, different signs subtract, keep the sign of the larger. So don't forget that. Same signs, different signs subtract, keep the sign of the larger. All right, so I've got 39 minus 22, which is 17. 39 is larger than 22, so we keep its sign. So negative 17. And then we divide both sides by 17, so x equals 1. Now this one can get a little bit more complicated when we plug that x into it. Pick either equation. I'm going to pick the lower one because it's just a smaller number. So 3 times 1 plus 2y equals negative 13. Okay? So we get 3 plus 2y equals negative 13. We subtract 3 from both sides, so we get 2y equals negative 16. Divide by 2, and y equals negative 8. Okay, so but I'm not done, am I? What do I have to do now? I hope you are saying that you have to write them as a coordinate point, and that is true. So we're going to write our point as 1, negative 8, okay, 1, negative 8, and remember that it's the point where the two linear equations that I started with, if I graph them, that's the point of intersection. It also means the point which makes both of the equations true. So if I took 1, 8 and I plugged it into this one for x and y, I'm going to get 22. If I plug 1, negative 8 into this equation, I'm going to get negative 39. But it has to be true for both equations in order for that to be the solution to the system. Okay? All right, last bit I want you to try. 3x minus 5y equals 15. 2x plus 4y equals negative 1. This is a scenario where you have to multiply both equations by a number because none of them are the same number. And we can't make them the same number without multiplying both equations. I'd like you to try this, finish it up, and bring it into class, and we will start here tomorrow. And then we're going to practice, 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 okay? All right, so hopefully you enjoyed getting back to the videos. I'm happy to be back doing them, and I will see you soon. Bye.